All right. Hello, everyone. Welcome to another episode of GPU Mode. This is going to be one of our last lectures for the year. Like next week is going to be like Compressed AI week. There's like a whole bunch of different stuff. So this is a talk I think we've scheduled like a while back, if I'm not mistaken, Vincent, like maybe like over 4 months ago. I'm not exactly sure on the details. But Vincent is basically a regular author of like incredibly beautiful like mathematical diagrams that describe like different ML systems algorithms. Vincent is also a PhD student at MIT, where like this is like a big part of like his research focus. So yeah, without further ado, I'm thrilled to have Vincent talk about his research. Vincent,
Thank you so much. Unfortunately, today my supervisor, Jolie Zardini, wasn't able to make it. So I'll show you what I think is a major problem in deep learning research and the sort of approaches we need to address it, and how by developing these approaches, we can do low-level kernel derivation and performance modeling much more efficient and even systematic. So this talk will cover a key issue, which is that deep learning models, despite being pure mathematical systems, where from start to end we have a mathematical formula, they lack a formal language of analysis. So if we look at the diagram on the right, that doesn't really show us what's happening. It doesn't really show the mathematics that's occurring. So this leads to issues. For instance, deriving flash attention took 5 years. And you have to note that flash attention already existed within the structure of attention. With a formal language, maybe we can approach these problems systematically. We can be given a definition of attention, and then from that definition alone, from the structure within the mathematics, we can derive these downstream properties, such as a flash attention implementation or certain probabilistic concepts. And we can use rigorous mathematics to do this. So in this talk, I will be covering a formal mathematical system to describe deep learning models and how they can be applied to systematic kernel derivation. So here we have an example for the transformer architecture. The transformer architecture can be re-expressed using this diagrammatic scheme. And as a formal method for deep learning models, there are various applications of this system. So kernels are but one. You can use a formal mathematical framework to start analyzing probability flows, how quantization errors occur, how training interacts with model size. We'll be using category theory. Category theory is the mathematics of abstraction and composition. As a result, things that are described with the language of category theory tend to be able to extend to these complex, large composed systems extremely well. And this has been the focus of my lab at MIT. And so we can actually quickly do a demo. And I can show you what these sorts of formal methods allow. So you should be able to see, yes, you should be able to see here this diagram. So this diagram has been automatically generated. So previously we just saw that these formalisms exist, but the utility of these formalisms is in systematic processes. So you won't understand this diagram yet. I'll go into that soon. But for now, you can understand that by establishing this language, we can do this automatically and we can derive these systems. So we can go into more detail there later. But now the background. What's the motivation for this research? What's the current state of deep learning? Why does this matter? So deep learning models are mathematical functions. We all know this. The next level equals some function applied on the previous level. But for some reason, we don't just use an oracle. And that reason is the computational limits that we have to work with. The design of deep learning models is inherently related to the task of implementing them. If that were not the case, oracles would suffice. So this was the major insight of AlexNet, which was the first network to really use GPUs and use them in parallel. Transformers came along next, which were able to do much the same process as RNNs, but in a much more computationally tractable manner by processing everything in parallel across multiple heads, in addition to other key features. And we have mixture of experts. Mixture of experts are a way of encoding the feed-forward layer that takes advantage of even multiple GPU systems. So we see that the fundamental design challenge of deep learning architectures isn't necessarily having this pure mathematical representation, but it is having a mathematical operation which relates closely to execution. However, deriving these low-level optimizations or even high-level where we decide to distribute across GPUs is difficult. Attention took 5 years for FlashAttention to be derived, and another 2 years for it to catch up to the Hopper architecture. So at the top right here, we see the sort of a high-level diagram of FlashAttention. And we have other cases like this. DeepSeek came out in 2024 and implemented what was a relatively standard transformer model, but by better co-designing the software with the hardware, was able to achieve incredible levels of performance. And a key fact is that the performance benefits of these algorithms existed in what was already there. It existed within the contemporary hardware. It existed in a close design space to existing algorithms. Yet we took all this time to derive it. So why is this problem so difficult? Well, deep learning models are pure mathematical functions. At a high level, I've said this a lot, but it's a very important thing to understand. Because it means there is a mathematical key. There is a reason these things exist, which lies in existing mathematics. So when we work with deep learning algorithms, we go from this mathematical description to an algorithm and finally to a low-level implementation. But there is some reason within that mathematics why that low-level implementation exists. But how can we discover this relationship? How can we readily go from a mathematical function to a low-level implementation? Well, the challenge in large part is because we lack formal representation methods. Currently, we often use linear algebra expressions, but they are insufficient to cover the nonlinearities within deep learning. For example, in this expression from the attention algorithm, of which axis does softmax occur, of which axis does concatenation occur, what are the sizes of these variables? How does one operation relate to the broadcasting of another? So this is a diagram from my first paper, which covers some of these ambiguities. And then given these standard ad hoc linear algebra or ad hoc diagram representations, it is difficult to see how they go to the low-level implementations we are after. And this is why deriving these algorithms takes so long. So the answer is we need some formalism for deep learning models, which can explain why methods such as flash attention are possible. And such a formalism would have other benefits for other forms of analysis. But in this talk, I will focus on low-level kernel derivation, because it is a field where diagrams can offer immense advantage, and much of the mathematics has already been sorted out. So what's our solution to finding a formal representation? Well, that would be category theory. Category theory is the mathematics of abstraction and composition. It studies composed systems that are generically built from objects and morphisms. Objects are anchors, morphisms are links. And so this could describe a graph, a family of functions interacting with each other, diagrams of a formal nature, or even algorithms. So here are some examples of category theory. This is from 7 Sketches. And so we can use categorical diagrams to show a cooking recipe, how one step relates to another, how the ingredients flow. A famous result from category theory is the Yoneda lemma. And so category theory, the language of category theory, can describe systems, but then also provide proofs about certain properties. And then we can go pretty in depth. Category theory allows for these diagrams to be constructed, and within the diagrams are encoded algebraic rules, and then complex relationships can follow. But to many of you that have heard of category theory, you'll be worried about the endless abstraction it is sometimes known for. So, why are we trying to apply category theory of all things? So, a way I like to think about this is something like group theory can on its own be extremely abstract, focusing on things which don't necessarily exist in the real world. It's a hodgepodge of theorems, or something like Riemannian geometry. But given something such as particle physics, where the nature of the problem are all of these interacting symmetries, group theory becomes the appropriate and correct language through which to approach it, allowing group theory, this abstract field of mathematics, to serve as a representation of the system and to provide theorems to work with it. And then the mathematics, the particle physics we have developed, the understanding of quantum physics that it has provided, has allowed for all sorts of implementations within the real world. So we see how an abstract mathematical system, given a problem which has the characteristics that system describes, can go from being highly abstract to highly applied. So with category theory, deep learning models are by nature highly composed systems, and we care about multiple levels of analysis. There is the functional level, there is the implementation level, there is the probability flow level. There are all these interacting levels for this composed system. So, and then category theory, as the study of composed systems and the relationship between them, becomes relevant and becomes a relevant tool to describe these things. So we can go from mathematics to a form of representation. Category theory provides the language in which we can talk about these systems and the tools and theorems to further describe them. So we see that this representation can then also go to implementation. So that covers the background of the talk and the justification for why category theory is applied in this realm, and ultimately what we can do with it, provide a formal system to describe deep learning models, as well as hopefully be able to go to low-level implementations. But then the question is, what is category theory? What is this thing we are working with? This talk will focus a lot on the mathematics. But for now, don't think about it as something too new. For now, we will just be describing some diagrams. So we start with a product category, which will be foundational to what we do next. So a category, a product category specifically, how do we construct it? Well, we have objects. Objects are anchors. They dictate composition. It could be sets for functions or nodes for graphs. And we will diagram objects in a particular way. We will draw a line with an arrow and label it. Next up, we have morphisms, which connect objects. We connect nodes with edges. We connect sets with functions. A morphism is anything which will be of this shape, something that goes from A to B, or it could go from A to A. And now to describe a category, we will have some seed morphisms. And from these seed morphisms, everything else is built. This isn't technically necessary, but is extremely helpful for representing a category, implementing it, etc. And finally, we can compose morphisms. This last one should be a C. When we compose morphisms, we We join them, and the intermediate object has to be the same, and then this forms a new morphism. You'll notice that this shape imitates this shape. Therefore, we have formed a morphism. So, in a product category, we can also stack things, and we stack things with a product. A product can combine objects into new objects and morphisms into new morphisms. Combining objects, for example, is assembling data types into a tuple of data types. And in that case, taking the product of functions would be running the functions in parallel. So we see how when we stack functions, we also stack their objects. Functions in parallel execute separately on the two inputs. And using a diagram such as this, we can represent that and how more complex systems are built up. Next up, we have rearrangement. Rearrangement has a very nice diagrammatic representation, but it might not be intuitive at first. So this is what it represents. Things like transposing, copying, and deletion are all sort of the same thing. When we transpose or copy or delete data, we're not manipulating the content of the data. We're just rearranging it. When we delete data, we have a forgetful rearrangement. When we transpose data, the rearrangement just would go 0 to 1 and 1 to 0. When we copy data, we rearrange it so that two things are the same. And we can actually express rearrangements in a unified manner. We have some sort of function that goes from the outputs. You can think of this as the variables we will have afterwards, the variable names we will have afterwards, to the variable names we had beforehand. And then if we have some variables, we can construct this rearrangement. Now, you'll notice that this rearrangement has the order swapped. So the name of outputs comes first to the name of inputs. And here it's the other way around. This is, you can find that this is the correct way to do it. And there isn't really another way. And this pattern will be very common and is very important and extremely helpful. So we have that. Okay, we have objects, we have morphisms, we have composition, we can take products or rearrangement. Now, what can we do with this? With this framework, we can start re-expressing something such as attention. We can go from this diagram, this ad hoc diagram, to something a bit more formal. So we have Q and K. We label the objects, which are sets. We label the morphisms, which are functions, and then we follow it through. You may notice this is the exact same. Categorical diagrams match very closely with what we would intuitively do. They match the flow of data. Category theory is a way of formalizing things that we very often are already looking at. But because of its rigorous structure, it allows for extensions to be developed. So what extension do we need for this one? Well, the one on the right isn't very helpful. We've already covered why. There is structure in this, which this diagram doesn't show. So we want to develop a way of showing that structure. And to do that, we will develop a specific category called the array broadcasted category. So this category will represent as its objects will be arrays or tuples of arrays. And its morphisms will be functions between arrays. And we will develop specific infrastructure to allow for broadcasting to be clearly expressed. So we'll start with the size category. The size category represents the coordinates which an array may take. We should all be used to this. It corresponds to the size of arrays. And so the objects will be that. And then what is the product? The product is assembling individual sizes into a multi-dimensional size. And so we have this infrastructure for sizes. We will show what morphisms in this category are very soon. But for now, we have sizes, and we can work with sizes. Cool. Okay, but what then? Well, arrays. We can use these sizes to define arrays. So an array is some base data type, FP16, the real numbers, anything else, and a size. And so we're basically saying for every coordinate that exists in the size, I have an instance of the underlying data type. So here on the right, we have standard representations, we could call them, where we have these grids and they represent values within an array, but we can develop diagrams. So how do we do this? What we do is we draw an arrow for the base data type, the underlying data type, then we draw the size above. So here we have A, and A is an object in the size category. And the size category's objects can be broken apart into a product of other objects. So we can represent this data type by this expression or by that expression. They're both the same because these two are the same. And note here that we keep the arrow on the base data type, but we remove the arrow from the top. The reason we do this is just do not confuse them with each other. Okay, next up, morphisms. Object to object, simple enough. Anything that goes in the middle constructs a morphism. And so this X might be that, and the Y might be something else. Or we can use this system to express this category. Next up, we have the product. The product is the Cartesian product, things going in parallel. Because we're using stacking without any separation to mean one thing, we develop this dashed line system to distinguish products from each other. This can then describe tuples of arrays and functions acting in completely independent parallelism. And so if we had this function and that function stacked together, it would be a function that takes a tuple and produces a tuple. So that's the array broadcaster category. It means we can re-express this as this. This is a bit more useful. We see that this is the size of everything flowing through the system. We can keep track of things a little bit better, but still, there's a lot of structure here that's missing. That structure is the broadcaster part. But anyway, for now, we can make an aesthetic adjustment. We'll use pictograms instead of names to represent key operations. So we use cups for matrix multiplication, which is akin to Penrose diagrams in physics. And softmax will be a triangle. It's a very important operation, so a pictogram makes sense. So now, how do we introduce the rest of the structure? How do we show the relationship between this queue and that queue and so on? Well, we need to develop infrastructure for lifting. So that's what's wrong about the picture on the left. We don't have this lifting information. So this lifting information is critical to things such as flash attention, because it is ultimately over this queue axis that flash attention occurs. So we can develop diagrams to clearly show it, such as this, which shows this relationship. This queue is related to this queue and so on, all the way from the end to the start of the operation. So what is lifting? What is this thing we're doing? Torch's VMAP doesn't give too much information, but we can provide a formal definition. So let's start here. We start with an operation that goes from the array on the left to the array on the right, like so. And we know that using our diagramming tools, we can represent it like this. Inputs, outputs, labeled with sizes. Now, when we lift something, we have F act across rows of a bigger array. So we have this. So here we have F acting on first, second, third, fourth row, etc. What will this look like? This will look like this will be diagrammed as a function acting on PA and producing PB. And we can do this wonderful trick, which is where to indicate that F is broadcasted over P, we just draw the P axis over the top of F. This modifies the input and output shapes in the correct way. and clearly shows the relationship between these two. So this is what lifting is. But how can we provide a bit more of a formal definition? Because we want to work with this. We don't just want to have lifting be a thing that exists. We want to show how lifting relates to things such as flash attention, or indeed some other analytical approach we want to take to deep learning systems. So we define lifting as follows. We use indexes. Or slices, rather. A slice is such as in PyTorch, where you extract a specific column or a specific row. So in this case on the left, we're extracting the third or the fourth row of the expression over here. And so we know that this fourth row has been generated by f acting on the fourth row of the input. And similarly, we can diagram a slice as so. So the slice on the y-axis, just as in PyTorch, then reduces that axis and then leaves the remaining axis behind. So this would be B. So this left-hand side can be represented like this. We have F lifted over P, and then that slice being applied afterwards. And what is this equal to? Well, it's equal to F acting on the fourth slice of the input. Or similarly, we can show it as so, with I, the slice, moving to the front of the expression. Note how this, the fourth slice, corresponds to this. So this correspondence over here has this diagrammatic representation. So this starts to show diagrams have some power. Not only does this p-axis correctly indicate the input and output types, it also allows for us to start performing algebra. And so this is how we can define a lifted expression. So here we have fp, and let's imagine we don't know what it is. But we can just say that given a slice over I, fp will be equal to that slice applied onto the input and the function f applied afterwards. So we can use f and knowledge of slices to define what fp does. And we have this slice naturality property, where a slice after an expression can be moved to a slice before, and both are mathematically equivalent. So in our attention model, we had softmax, broadcast over Q. What does this mean? It means that a slice after the expression becomes a slice before. For element-wise expressions, we have the axes going at each side. So we have both axes going through. This means that a slice, so if I ask what is the ij coordinate of the output, is equal to the function applied onto the ij coordinate of the input. And so here, just a quick note, this is the product of size 0. So when we lift a base data type by a product of size 0, we get an item. It's a lone value. Also, you may have noticed that we're not writing the base data types much here. We can keep it implicit. We know what's happening. For lots of this analysis, it's not directly relevant. So we have slice naturality. Now let's go back to the size category. What are the morphisms? What possible morphisms would we want to apply onto the size of axes? Well, affine transforms. This definition is a fair amount, but all you really have to know is that we're restricting ourselves to affine transforms of coordinates. This will become very important because it allows for some very nice theorems to be derived later on. So anyway, let's keep that on the back burner. Next up, after lifting, we have reindexing. Reindexing is where we lift, but the output slices don't correspond to the exact same input slices. So this could be that the ith output slice corresponds to the eta ith input. Exactly. We have this sort of pattern. So what does this look like? Well, this would look like this row produces this row, and this row produces this row. So how can we clearly define this? Well, we say, again, ith output corresponds to eta I input. So eta maps from 0 to 0 and from 1 to 2. This could, for example, be the dilation in a convolutional network. How do we diagram this? We diagram it like this. So, well, we know that the input here is QA, so we can chuck QA down. The output is PB, so we can chuck PB down here. And then we have some slice acting on it. So this slice is in P. And then we know that this should be equal to that. So here we have the eta I slice, and then this produces A, which F can act on. So what do we put here? Well, we can just put eta here. So if we have eta above an expression, it maps from, so eta maps from P to Q, and here we have P to Q, and we put eta here. So the orders are flipped. What it means that I, effectively, it goes left, and then it interacts with eta to make this slice, which can be moved behind the expression. So we have this. We know what F is. We know what this is. It is just a slice. We say that this is equal to that. So this defines a reindexing. So what can we do with reindexings? Why have we gone through all this trouble of defining them? Well, take transposing, for example. What is transposing? Transposing means the ij coordinate of the output is equal to the ji coordinate of the input. These two swap around. Previously, we defined rearrangements as a fundamental component of these product categories, and here we're using them. We're rearranging the indexes to swap around. Then we're using that with a reindexed lift to define what a transpose is. So that's one example. We can use this reindexing terminology and this rearrangement terminology together to present to show that transpose is just a specific instance of this thing. Furthermore, we may have something like matrix multiplication. Matrix multiplication is a bit more complicated, but fundamentally, we have the ij output is equal to the I slice of the first input segment and the j slice of the second input segment. What is this operation that goes from ij to I? It's deletion, projection into the first dimension. So this can also be represented as a rearrangement. Same with this. So we can use rearrangements together with reindexing to define these operations. But we can also do this a bit differently for matrix multiplication, I mean. We could have that the ij output is equal to this slice rearrangement. And with diagrams, this can be clearly shown. We show how j relates up to x and how I relates to q. And so here, the rearrangement of projecting into each of these segments is implicit. And we can effectively just trust the diagrams to show us how things are defined. So now we've built up this infrastructure. What can we do with it? Well, we can take attention and re-express it as a series of lifts and reindexings, giving us this expression. So over here, we can see we have Q and D, and this axis travels all the way through. So does this one. We don't use optimization. So what does this mean? Well, let's have a look. We start with our expression. We show the broadcasting. And let's take some indexes and let's see what they do. So they'll move up, across, across, and across. So what did we just do? We showed how this expression, how some output relates to a specific input. And furthermore, how this is, furthermore, these outputs are independent of each other. So what does this mean? This means that we have the output of the expression is equal to a series of independent calculations. What does this mean? Does this mean that we just derived flash attention like this as a way of decomposing attention into a series of independent operations? Well, no, but sort of. We'll need a bit more infrastructure for that first. So, but we got close. And so, just quick. So next up. So this has been a lot already, but hopefully most of this should be understandable. We use lines to broadcast expressions, and we use the shape of lines to show how output indexes relate to input indexes. And this can decompose something into independent expressions. This is not quite enough to derive something like flash attention yet. So the rest of the talk will be in two parts. First, I'll go over what I like to call the napkin method. This is shorthand derivation. So this is without too much of the formalism. The napkin method is what we will build up to with the second part of the rest of the talk, which will be quite mathematically intensive. Going over the napkin method first, I think is a good way of firstly getting the diagrams to be a useful tool that you can start using, and to understand why deriving this mathematics is so important. So, what is the napkin method? It is the fact that given this diagram, we can derive flash attention at a high level because we can see the independent operations taking part. Okay, so how do we do it? We begin with a high-level diagram, such as the one you see. So first we know there is this property of certain operations that they are streamable. And when an operation is streamable across an axis, it means the input to that axis can be fed in chunks and accumulated at a lower level. So softmax followed by matrix multiplication is an instance of this. So we can relabel the x-axis to be streamed and to be sent down in chunks. And then this axis, because it travels all the way through the expression, we will have the streaming take place. So we can do this. And so now this SX figure, this represents the size at the lower level. It represents the chunk size. And now what do we do next? Well, previously we showed how an index from here flows all the way through to the start. So instead of executing all the Q values at once, we can execute them in independent chunks. And we label that GQ. So what do we now have here on the right? We have a sub-algorithm. This sub-algorithm says, this diagram says something. What does it say? It says that we are distributing into blocks over Q, each of size GQ, independent operations. And for each block, we are streaming the axis X in chunks of size S of X. So what we can then do with this is this shows the amount of memory on chip. It shows the amount of transfers that are taking place for each of the sub-algorithms, and it shows the number of sub-algorithms we have. The number of sub-algorithms will just be given by the total size of Q divided by the individual chunk size. So we can have that. But there is a restriction. The bigger GQ is, we have to keep GQ below a certain level as to not violate lower level memory. So we have to take that into account. But given that our stream size can be small enough to ignore really, we can get this expression. So this gives an upper limit to the size of GQ. Okay, great. So we have this diagram. It represents a low-level algorithm, and it allows us to get the maximum memory that would be on chip. But we also want to, for flash attention, the big insight is being able to reduce the total number of transfers that take place. So to calculate this, we will look at the transfers per tile, and we get that by looking at the size of the inputs and outputs to the expression. So we have the number of loads and the number of saves. And from this, we can calculate the total number of transfers that need to happen. We multiply the number of sub-algorithms by the transfers per sub-algorithm. And taking these two together, we get an equation. And furthermore, we can find GQ because of our previous condition that the maximum memory cannot be violated. And from this, we simplify the expression and we get to the same performance model as the first FlashAttention paper. So, what have diagrams just done? We've started with a diagram and then applied these tricks, basically saying that we can stream and we can tile, and that these strategies travel across axes. From this, we have derived a performance model, the same as the one from FlashAttention-like. And we have derived an algorithm which chunks the Q values to be operated on in parallel and chunks the x-axis to be streamed into each tile. So we have derived the algorithm at a high level from FlashAttention-2. So in me and Joela's prior work, FlashAttention on a Napkin, we developed these methods and then we applied them and we saw how deep we could go. And using these diagrams, you can derive a very low-level algorithm that says the specific operations that must take place, how axes must be split in parallel to be streamed, etc., and can even give insight into the number of clock cycles required per operation. However, these methods have up to now been diagrammatic. They're algebraic tricks that we can use. But there is immense value in not just having the tricks, but having the tricks be able to be systematically implemented, to be rigorously defined, to not just be, you can do this with a diagram, but to actually be, this is what the underlying mathematics represents. And this is a correspondence to an underlying algorithmic process to build a formal tool. So that'll be the next section of this talk. We've introduced these diagrams. We have shown a specific instance of how they can be used to look at a method such as FlashAttention. But what does this all rely on? What mathematics have we been using? How can we be confident that it even makes sense? Well, for that, we will turn to broadcasting algebra. So, we have introduced lifting. When we lift, we can take an array morphism, a function between arrays, and a size morphism, an affine rearrangement of coordinates. Well, not necessarily rearrangement, it can be more general. And then we can take the array morphism and stack the size morphism on top. And now what does this lead to? This leads to the expression on the right. And because we're using category theory, there are some useful tools. I haven't introduced you to identity morphisms yet, but think of identity morphisms as saying whenever we can use a morphism, we can use objects when we can use morphisms, which sounds weird, but we have already used it. So for instance, if our size morphism was just the identity mapping from P to itself, we have a standard lift. We go from P to P. Instead of the index going from IP to eta IP, the index just goes from IP to IP. We see that lifting is a specific instance of a reindexed lift where we use the identity size morphism. Additionally, we may have an array identity and a size morphism, and then we will generate this expression. What does this mean? This is a pure rearrangement of coordinates. Means an instance of this that we have actually already seen is for transposing, but copying would be another instance. In these cases, we're just saying this operation doesn't do anything to the data. Nothing is happening to the data. but which coordinates refer to what is changing. And so in this framework, we have distinguished between operations which change data and change the content of data, and operations which just rearrange data. And we have shown how they can be represented together as one unified concept. So this allows for a general description of the operations that take place in deep learning models, with careful attention being paid to how data is rearranged and manipulated. And furthermore, provides the key insights we need for deriving, say, low-level kernels or studying how probability evolves through a system. Because these characteristics, such as kernelization, stem from the fact that data is, in part, just being reindexed rather than being manipulated, and is being reindexed in a specific way that this method can accurately describe. So, what does lifting give us? Well, it's category theory. We care about composition, right? Lifting gives us this really powerful compositional property. When we have two expressions next to each other that are both lifted, we can join them together. The composition of two lifted operations is their composition lifted by the composition of their reindexings. So here we have used this notation, the semicolon. This represents forward composition. Don't worry about it too much. Basically says we do F and then we do G. You can contrast this with the circle notation, which is we do mu and then we do eta. So it's just swapping the two around. It makes these categorical expressions just a lot more coherent to work with. And so what do we have here at the bottom? Well, we have the top. But how? Well, if mu was the identity of P and G was F and F was the identity, we get this. And then on the right-hand side, we have if mu was eta, if G was the identity on Y, we have this expression. And these three all interact with indexes in the same way. If I queried any of these expressions with an index, I would get the same result. Indexes form what is called in category theory a family of projections, meaning that if two things are equivalent over a family of projections, they are necessarily equivalent. So, and now we will get to broadcasting. Okay. So, broadcasting. With matrix multiplication, we saw that the two inputs took different reindexings. This can be seen as a more general case of lifting. We can express this in terms of liftings, but being the more general case, it is the thing that we want to focus on. It is if we can describe how broadcasting interacts with kernels, kernelization, index flow, etc. We can describe kernelization in general. Not only will we have described the basic cases of one input, one output, we will have described multiple inputs and a single output. We would have described, and by focusing on reindexings in general and not just rearrangement reindexings, we can describe both something like attention, where we can mostly get away with just rearrangement reindexings, or we can also describe convolution, which uses addition as its reindexing. So we want to describe the general case, and the general case is broadcasting. So what is broadcasting? Just think matrix multiplication, or that specific instance. What we did there, that's what we're talking about. We're saying that each input had a different reindexing applied. And in order to represent this, we will use this shorthand. We will say A to I, in the case of matrix multiplication, projection into the first, projection into the second. And then here, we're representing a product. So this product is xi, qi. So this is a product of multiple arrays being represented here by this notation, the I. If we have this I here, it means we're working with all of them at once. So we just have this notation, which is said to be definitionally equivalent to this. Great. And then we can drop the pi symbols because we know that if we have these lingering eyes, that it means that there is a product happening behind the scenes. So what algebra can we do with broadcasting? Well, broadcasting is just lifting re-express, so we can do this. If we have this expression, f broadcasted and then some mu, we can move mu into these expressions. Again, this is a consequence of both the expression on the left and the right doing the same thing to all indexes and therefore being the same. And so we have this equation. Well, it's a diagram, but the diagrams are equations. It is very important, and we will use it in an innovative manner. Kernels and tiling. Okay, we've just covered so much algebra. There's more algebra to come. What we've covered so far is what can we do with diagrams? How can we look at indexes, rearrangements, underlying functions? How can we mesh them together? How can we study the flow of indexes? How can we come up with these nice diagrams and equations to represent it? Why did we do this? To describe kernels, of course. But how can we use this to describe kernels? Well, first, let's be clear about what we want a kernel to look like. A kernel is, in essence, some operation which splits data into independent tiles, an operation acting on those independent tiles, the sub-algorithm, and then an operation joining the outputs together. So if some f can be re-expressed as so, it means we have developed a kernel. We have said that f could equivalently or correctly be executed as a series of parallel operations. And now, just as we did with the napkin method, the amount of data required for x kappa is less than the data required for x. And thereby, we are able to efficiently do this at a lower level of execution. We will achieve kernelization using tilings. Okay, this diagram, it's amazing, but you need to know what's going on. How will we do this? How will we show tiling? Well, we have our reindexing tools. What does reindexing do? It could take an operation such as p kappa t to p and then generate a split xp x p kappa t. This is what we're after. We're taking x and then we're splitting it. So here we're taking x and we're splitting it. Well, we're taking xp and splitting it. What reindexing do we need to define this? We need something of this shape, right? But why this portion on the left? Well, this part on the left means we take the value of p, we just take it just as an identity, so we can use objects to represent their identity morphisms. Then we take our grid index t, so this represents our location on the grid. We multiply that by some stride, and we add these together. So using this, we can go from a coordinate in the grid, which has both the local coordinate within p kappa and the grid coordinate within t, and we can combine these to get a coordinate in the original array. So taken together, this allows us to go from a big array into these subarrays. The subarrays are indexed by t. The location within the subarrays is indexed by p kappa. And we can do this using a reindexing. So we have indicated that this operation doesn't change the underlying content of the data. It just puts it in different spots, or it uses a different system of coordinating the data. And that is represented by the reindexing. So in this manner, we are able to define splitting an operation into, or splitting an array into subarrays using this reindexing tool. Okay, and now some tiling algebra. This is, what's the essence of this? This mathematics is here for you to indulge in if you so desire. But, what's the essence? Well, we're saying that reindexing is composed in quite a nice way And this is a nice way to express a tiling. So we say that if we have a tiling and we follow it with any affine reindexing, we can rearrange it into this. We use this sort of notation. This notation here basically just means that every one of our affine functions is some map from naturals to naturals, fundamentally. But when in the category, we have to label the domain and codomain. When we do this, we are restricting that function to a specific range and image. So eta p is just a way of showing this restriction. So here we have our original form, eta on p. Eta p is the size of the full array. And here we have eta on p kappa. This is eta acting on a subarray. This is a tiling that comes beforehand, a reindexing afterwards. And then this is a reindexing that comes beforehand, and a tiling that occurs afterwards. Just a reminder that these, being objects, represent their identities. So this tiling, how is this stride derived? It is derived from kappa, so the kappa stride passing through the linear component of eta. So we already get the offset of eta from here, and then we have the linear component. We can test this by tracing it. Eta applied there to there, plus kappa lambda eta gives us that, which is equivalent to the other side. So because of the property of, this is why we chose affine functions, because we can do this rearrangement, where a reindexing or a tiling followed by a reindexing can become a reindexing followed by a tiling. Their order can be safely swapped. So what does this do? This allows us to go from this expression on the left, which is a broadcast followed by a tiling. And just using the broadcasting algebra, we can do this. This just uses the lifting algebra. We merge these together, and then the right-hand side can be re-expressed. So then we go from this to this. Now this means, just as we did before, the reindexing comes first, followed by the tiling. And so what does this mean? Well, it means that we have taken f, which operates over degree p. It is a p-fold broadcast. And now it is a p kappa-fold broadcast. This is the big function, and this is the small one. This is the sub-algorithm. So these two are equivalent using algebra. And now we're going to come up with diagrams to easily show this. So we'll just do that. We take this t-axis and we just represent it as a bounded box, a dashed bounded box. And then we know that this shape means we have a tiling which uses the t and gets rid of it in the process. So we have this. So an expression followed by a tiling that is tiled over the same axis, so this kappa tiling happens over p, becomes a tiling which includes f. This is tiling subordination and is how we derive kernels. So for join, so remember how kernels had a split and then a subalgorithm and a join. If the tiling is invertible, which is the case if the stride matches the size of the subalgorithm tile, then we can come up with a join. So this join goes from a series of tiles to a single array. And then if we apply this join onto the end of both expressions, because this holds, we end up with this. So this is our function, our original function. And we have just derived a kernel. This is a kernel. We have a split. We have what each individual subalgorithm does, and we have a join. This is general. All that has to be the case is that the tiling occurs over the same axis over which the function is broadcast. And so as a result, this tiling can absorb something that comes beforehand. So if we look over here, we have a tiling afterwards. That tiling afterwards can subordinate G, which can then furthermore subordinate f. Tilings, and by expressing tilings in this way, and by allowing for reindexing, this affine mathematics, the mathematics of broadcasting, all of this, what this allows us to do, the reason we have done this, is so that we can take a tiling, we can show that it composes, and then we can encompass multiple things. This is a fused expression. This is how we can generically represent what it means to fuse operations, and therefore only have to execute them once. This block serves as a sub-algorithm which executes both in sequence at a lower level. In this case, there doesn't have to be communication with a higher level. If we can decompose an expression into these tilings, we can fuse in a fairly straightforward manner, and what we are left with is a fused kernel. So that is why we have developed all of these tools before, all this algebra. And furthermore, we can do this sub-kernel trick, which is where when we merge things, these expressions can also be turned into kernels. So this represents this is multi-level kernelization, because this can be transformed into this. We know this can happen. And this matches closely with, for instance, when you're doing something such as attention and you move matrix multiplication to a warp group level rather than registers. This represents a hierarchical process. So using these tools, we have shown how a kernel is really a special form of reindexing, and that fusing kernels is a special form of composition. These insights are very category theory flavored, because the language of category theory that allows us to express deep learning models in this array broadcasted manner then leads to these tools. But there is one aspect of kernels which we haven't looked into yet, and that's streaming. Streaming is when, for example, matrix multiplication, we don't load the entire input, we load the input in chunks, and then we add the chunks together. As covered in Flash Attention on a Napkin, streaming has this general form. Whenever a function can be re-expressed as the operation on the right, where we have the function act on a portion of the s-axis, and then have the rest of the s-axis be accumulated, so it can be expressed like this. So what we're doing is we're splitting this axis, giving us two arrays. We're feeding one of them to the function, and then we're feeding the other one to an accumulator, along with the output of the previous function. In the case of matrix multiplication, because matrix multiplication is associative, we can do this. We can take the input, we split it into chunks, we feed one chunk, we take the output, then we sum the output with another chunk from the next input. So we can organize our expression in this manner, reducing the amount of data that has to be kept at lower levels. If this equation holds, or if this diagram holds, they're the same thing, we can do this rearrangement, where we recursively expand the expression. So this means this is sufficient for streaming to be of any size we really want. We can do any number of streams. And so streaming looks like a sequential tiling. Instead of having the function, instead of having this function, we express it in this manner, where this input is known to be a collection of chunks, a collection of tiles. So it has this additional dimension. So we have S and that, and then we have a tiling. So remember, this is what we use to indicate that something is a tiling. We have a tiling which splits this into chunks, which has this additional grid axis n of sigma, and then this is fed as the input instead. So this also forms a tiling. So what can we do with this? So suppose we had some function followed by a function with a streamed input and then we have a tiling afterwards. We want to subordinate the function into the tiling. Well, what can we do? We can subordinate G into the stream tiling, and then we can subordinate the entire expression into the kappa tiling. So this means that this aspect is run n times t times. This, everywhere that's not covered by the stream, is only run t times. And the tools we have developed where we can subordinate things cover this case. And furthermore, we can subordinate things into the stream component of an expression. So we have just covered, and this is the general case of a kernel. In general, a kernel will have some tiling, some parallel tiling, as well as some sequential component. And both of these can be used to subordinate expressions that come beforehand. But there is a very important case to consider, and that is when expressions are misaligned. Because tiling and streaming can only occur when we have appropriate index flow. What if the indexes don't flow in a trivial manner? So what are some cases of this? Well, we have weaving. Weaving is when we don't just have a straight up broadcast. Or straight up lift. We're not just lifting to the top of an expression. We're lifting in between, this sort of thing. This is hard to express with equations, but with diagrams and code, it's quite straightforward. We have this axis, goes through this, and then relates to that and to that, right? In matrix multiplication, you may notice that if we were just lifting, x would go here, but it actually goes here. So here we have also used weaving. So we have these cases of weaving. We have cases of weaving. Over here, we also have the case where these aren't tiled over the same axes. This is tiled over here, but this is not tiled over that. So how do we deal with these cases where things are weaved and the tilings don't align? Well, you remember that tiling was possible because of index flow. When we have aligned index flow, we are able to do a tiling. And when we do this, we relate the output tiles to input tiles the output tiling to input tilings via the linear component of the affine reindexing. So this would be the standard case. When we go towards implementing this, what we will do is we will define a grid index along, or a grid axis along each of the axes over which we are tiling. We will generate some size of the tile, and we will use a simple scribe. We will take our grid index multiplied by the size, and then that gives us our tiling. And then this is defined for each axis, and then that passes through everything. So there's a bit of a better way to show this, and that is like so. So what we have here on the right is we have G. This is the top axis, the second one, and the third one. T is a tiling, or tau. Tau is a tiling. That tiling doesn't care about this axis. It cares about this one, and it cares about that one. It will develop some sort of stride in each direction. So we have that tiling. Then the tau tiling will pass through mu and then become some sort of tiling on the input. If I have an axis, or if I have a coordinate over here, it may map to a coordinate over here. There is some sort of linear transform here, mapping from a coordinate along these axes, a slice along these axes, to a slice along these ones. That's what it means for this to be broadcasted. There is some clear relationship between output and input slices, and it's linear. And a similar thing happens for F, but it happens in a different way. So we have the grid coordinates here mapped to grid coordinates in this plane. But pi maps grid coordinates in this plane to grid coordinates in this plane. So we can't just say, oh, we're just going to fuse these two together and have all the indexes flow through. No, only some of the indexes will successfully flow through. We have limited index flow support. And because of this, we have to remove this tiling. So we remove this tiling and all further effects it has because it's not supported over here. Similarly, we remove this tiling because it's not supported by G. So, and by the way, these are generic expressions. So we don't really care about the pattern. We just care about how outputs relate to inputs. Okay, so we abandon the axes, which aren't fully supported through the entire expression. And then we are left with these. This axis was supported by tau and mapped through. Then this axis was supported and mapped through to the very end. And so we see that this axis actually influences both of these. And then we isolate the components of the reindexings, which allow for this. Overall, what does this allow us to do? This allows us to take an expression and then develop fusion even if we don't have perfect alignment. And though this process is complicated, it's systematic. If we have represented each axis as having some tiling at some kernel level, and we have defined our reindexing affine operations, we can implement this. And once we have implemented it, it will derive fusion. It will derive a generic case of fusion automatically for us. So even though this is complicated, it's systematic and allows for fusion even in complicated cases to be systematically implemented. So let's look at what would happen in the case of attention. Suppose we have developed two kernels already. We have developed the QK matrix multiplication, and we have developed the attention followed by matrix multiplication. So we have these two kernels. So what would fusing these two look like? Well, we know that indexes are supported here, and they're supported here, so this flows all the way through. And then this sigma streaming split can then subordinate this pi1. However, this zeta is not supported. It can't just join a stream. We already have a stream for the kernel, so we must remove it. So we see here that sigma can be used for pi1, and tau0 can be used for pi0. And so then we keep all the axes which are supported by the index flow of both components, deriving the high-level kernel. So this derives the fusion. We have the sigma, the streaming, happens over everything which interacts with this axis. So it happens like this. We have kappa, which is tiling Q, and this should be d kappa. And we have K1, which is tiling this, though we don't use that for implementation because it doesn't impact the result. Okay, so we have this method, and we can systematically fuse even misaligned kernels. And recall that we did this in a general way, even though here we are just using rearrangement reindexings, which are the simple case. In practice, we can use more complicated reindexings. So what does this allow us to do? This allows us to search for optimizations. Category theory states that this sort of product category system we're working with can be re-expressed as a graph. And so therefore we just need to code up the graph. Then the graph can start fusing things together. And then we can have these higher and higher level fusions. So we see that this method also allows for this optimization search to occur. Okay, but we need to judge the performance of these optimizations in order to actually do a search, right? Like this is just searching through them. We don't know how to compare them, which paths to choose, and so on. So in order to do performance modeling, we will first need hardware modeling. GPUs are complicated. GPUs have multiple levels. We have, high level, GMEM, then L2 cache, we have L1, we have all these transfers between levels, within levels, but fundamentally, we can condense this. What we really care about is this. We have these different levels. They're connected to each other. If they're connected, they can transfer data. And certain levels, such as tentacles or RMN, pure RMN, can execute operations. So as we show in Flash Attention on a napkin, this hierarchical view can even encompass, like if you can transfer across levels, that can be condensed into this. The equations are much the same. So we can take this complex GPU hierarchy and we can represent it like this. This is what we need. This is what we care about. And so furthermore, because GPUs have this recursive structure where we have high level with lots of memory, low level that can execute things, we can condense a lot of this information into a two-level model where we have a high level and a low level. And if we have derived some optimization for two levels and recursively apply, we can get an expression for, say, the total bandwidth across all levels by just summing a series of expressions together. So because of this recursive structure, we can mostly worry about two levels, at least for now. Once we want to do implementation for warp groups and so on, you will have to focus a bit more on a multi-level system. But we've already developed lots of the infrastructure for multi-level systems, so we're covered on that front. Okay, how do we represent this within our data structure that we have presented? We will do what I like to call base data type smuggling. So arrays have two components. They have a base data type and they have a size. So far, we haven't used the base data type. We haven't even diagrammed it because it's not necessarily relevant. But it is a perfect place to put lots of information. For example, we can say that the base data type isn't just the real numbers, but it's the real numbers and a location, or it's the real numbers and some quantization. So using the base data type, we can say that something is a real number located at this level with this quantization, etc. Furthermore, remember the expression we had for taking an array morphism and a size morphism and making a new array morphism by lifting? What we can do is we take as the array morphism, we take conversion between data types. And that conversion would be going from one level to another, and a split tiling, which is what we already used. And then we take this lift. And now what this lift is not only do we split P into P kappa, but we also change the data type in the process. So this data structure, this construct, can represent the process of moving to lower levels within the GPU hierarchy, or moving up levels, whatever we want it to. And so we can take our derivation of a unified fused kernel, and we can add this information. We'll just do it by coloring it. And so now, this expression. What is this expression? This expression for which we have all the tools to derive this. We can handle misaligned fusion, we can handle streaming, we can handle all of this. And now we can also describe the level at which operations occur. What's happening here? We've included information about lower level sizes. That's present. We have included information about transfers. So this is transferring data of this size. How many times is data being transferred? Well, it's being transferred T kappa times because it's located within the kernel. So everything happens a T kappa number of times. What about this region? Everything in this region is happening an n sigma number of times on top of T kappa because it is part of that tiling. So this expression contains everything we need to derive the high-level performance model of flash attention. It shows the number of times things occur, it shows what is occurring, and so on. So we can now move to performance modeling, now that we've covered how hardware can be represented. For performance modeling, we care about choosing the optimal sizes. Given some size, we can use composition. We can use decomposition to find memory usage, compute, bandwidth, etc., because these have a compositional structure. Doing something t times multiplies the amount of memory users by t. Well, having something be t times bigger. Memory doesn't increase as you have more tiles in the kernel because memory is only relevant for one tile. But for compute and bandwidth, which we care about at the level of at the total level, at the level of the entire algorithm, it does scale linearly as we have more tiles. So we can come up with expressions for memory, we can come up with expressions for compute and bandwidth. And so these expressions go all the way down to seed morphisms because all of our compositional tools, all the ways to build things up, can be decomposed. Ft becomes T times H of F. So this is for compute or bandwidth. And so this number is different across the kernel. But again, we have the tools to represent this. All this is represented. And using the compositional structure of category theory, we are able to express things such as bandwidth and memory usage in this decompositional manner. So we have the tools to do this. So category theory allows us to do this performance modeling. We have developed the entire framework we need. We have shown how category theory provides the compositional algebra to think about kernel fusion, how we can use array morphisms, tiling, like all these things come together in producing this performance model, which has this performance model, these optimization, systematic optimization tricks that ultimately are just one application of the advantages of formally representing deep learning models. And so I think with that, now that we've got all the way down to performance modeling and hopefully convincing you that category theory is sufficient to cover it, that will be the end of my presentation for today. Hopefully this will serve as a helpful resource for you to get attuned to this type of algebra and this type of approach. And hopefully it will motivate you to, as well, look into these formal methods for describing deep learning systems and find applications within deriving low-level kernels, performance modeling, and beyond. Thank you.
Sweet. Thank you so much, Vincent. This is fantastic. So I guess there was a couple of questions in chat. I can go through them, and I had a couple of my own.
That would be great. Sorry, I didn't see the comments.
Oh, no worries. So if I do this, do you see it?
I haven't looked too much at category theories and types. I think, so you can use category theory for compilers, you can use category theory for abstract type analysis, and I believe, though I'm not certain, that that's often used for compilers, CPU programming languages, etc. I think that compilers, CPU programming, etc., that uses a different dynamic to GPUs. GPUs are in many ways simpler. The degrees of freedom are smaller, and the things we care about are quite limited. I covered arrays and broadcasting because that's most of what we care about. So I haven't worked too much with stranger types. No, and so far it hasn't been necessary, but there would definitely be ways to integrate it into this. Category theory allows for those compositional tricks.
All right, another question by George.
I believe it would have. I'm obviously biased. So I'm not the right person to ask, but the trick so these diagrams, they don't actually derive FlashAttention-1. They directly derive FlashAttention-2, which is already a good sign that they point to some underlying value within the framework. They use very similar methods to matrix multiplication. So like matrix multiplication, the optimization for it as well, it's just you just label the axes. And with flash attention as well, like I developed the diagrams before I came across flash attention. And then when I saw flash attention, I then developed these methods to look at flash attention specifically. And the methods ended up being literally just line go all the way through relabel line. So yes, but of course I probably would have like the way these things are, everyone misses it. So
Another question from Enkidu.
no, I don't think you could prove it. This is more like also on the flash attention note. Flash attention uses a lot of other tricks which these don't cover. Flash attention is like extremely smart. Like there's warp group things. There's like in flash attention 3 you like rotate the input, so that's not like all covered. Like I'm not saying that this is like wow, like so amazing. It's just like for the high level view. You can do the low level, but that's not fully formalized yet, and I don't think I would have been able to do that without doing ad hoc. Anyway, sorry, the previous question, I'll cover that. I missed it.
Yeah, I think
smaller set operation. No, this is a language. So the language describes what the language has been developed to describe. For a smaller set, the idea is as we come across more kernels and more tricks used by different kernels, you then develop the language to implement it. So over time, you incorporate more and more tricks. So one of those tricks, for example, is reduction. So in reduction, you parallelize an associative operation. Streaming is already covered. Streaming is where you sequentially do an associative operation. So for example, the trick of going from streaming to reduction is, in theory, should be straightforward because instead of sequential, we do it in parallel. But I haven't developed the mathematics for that yet. And that is an instance of, as we come across more things, we develop more language to describe them. And then the hope is if we come across a brand new kernel or a brand new algorithm, just like that, we can apply all the tricks that have already been developed. But no, they're not able to tell this is like the set of all tricks that are possible. It is to be able to mathematically describe tricks so that they can be generally applied. Yeah, thanks. Good question.
Yeah, I mean, how do I put this question? So one of the interesting things you brought up is that like just because you've sort of layered things, it seemed that a lot of like the sort of maybe like 80% of your talk or so is actually like hardware independent. Like basically the sort of like the formalism of the hardware is like then thinking about like, oh, like GPU specifically, you need memory to be transferred between GMEM, L1, L2. But then otherwise everything else is sort of like not that, and potentially would be kind of interesting for people to reason a priori what kinds of hardware you might need. Is this like something you've thought about?
Yes, it is. The hardware is abstracted away. The methods are very intentionally developed to be hardware independent, but I think that overstates the amount of effort that's required to make it hardware independent, because these GPUs, they're all sort of the same. You have hierarchical processors. Each has memory and can execute an operation, and they can transfer data between each other. Like that, they can execute different operations. They have different resource costs for different operations, but the scope to describe the hardware is limited in that way. It depends on the depth you want to go into, but a priori reasoning about what hardware would be good, I think, would be extremely informative. In this talk, I covered lots of the mathematics, but I didn't cover too many of the insights. And one of the insights is for bandwidth. If I want to minimize the amount of the time I'm spending sending data, there are two factors to consider. There's the speed of my bandwidth. Of course, if I transfer bandwidth faster, it's faster. But there is also memory size. The bigger my cache is, the less redundant loads I have to do. And there is a trade-off between these two when designing a GPU, because the more transistors I allocate to one task, the less I have for another task. And this trade-off between how much memory I want and how much how much my bandwidth speed and how much my cache influences the speed of an operation, that varies between algorithms. And so some algorithms are more or less sensitive. And I think those sorts of insights so this actually goes into Gioile's work. He's looking at category theory, doing these sorts of co-design problems where you relate the functionalities and requirements of, say, the algorithm to the functionalities and requirements of, say, the transistor count for a GPU, and integrating that into a cohesive system. So yes, this is something we're very keen to work on soon.
For my other question, it might be easier to share my screen, so I'm just going to do it quickly. So like some of your later diagrams like really reminded me of this view in the NCU profiler, where like you basically run a real workload and then you monitor for all the different kinds of memory, like how much data is like being moved through it, and then like what's the bandwidth of it. Have you potentially looked at like validating like experimentally like what memory model you predicted analytically versus like what was seen in practice, and any interesting differences you might have learned from this kind of exercise?
So that's something I really want to do. Like I really want to, because these are like equations and they're the same expressions from other work. Um, if we can like just test these and see how these like derive like order of magnitude calculations, how well they correspond to empirical tests would be extremely interesting, I think, because then you can start, you improve the model, right? So that like whatever coefficients you need to add, you perfect them through lots of empirical testing. And at that point, you can just be given an algorithm and then do this high level performance model derivation, then do the adjustment process as indicated by prior empirical testing, and then just have a really good idea of how many resources it will require to run. So I think that would be a super valuable task to do. We have used this method to implement an attention variant from scratch before. So that was in a paper. I can see if I can get it. I'll. But yes, I can find that and get and answer a few other questions.
Yes. So I mean, like what's interesting about simulators is like the cost of profiling on an individual GPU isn't very expensive, but it gets very expensive like once you go like beyond a single node. What sort of brings me to sort of my second question. This is a bit of a more ambiguous question, but like I'm curious to hear your takes, and I'll just ask it regardless. Which is, I remember like 10 years ago there was kind of like a big sort of resurgence of category theory. Like the idea in AI was like, well, they're all functions, we could compose them. It just sort of felt like natural. And then that wasn't like basically for like another 10 years, like the idea sort of like died off a bit. But they made like a very strong comeback when layout algebras became really important, both in libraries like Cutlass by NVIDIA, and also when doing like sharding propagation rules for distributed tensors. And I'm sort of curious, like if you sort of have any observations, like basically was this sort of a natural transition? How come is it now that these ideas are like basically coming in full force? So yeah, any sort of comments on this history?
So two things. Coupless is interesting because it seems like it wants to be. Okay, I'll actually cover category theory and why I think. I spent some time in the talk covering why category theory, right? Like this is like an abstract field of maths, right? Like topologists consider this to be that's too abstract for me, no thanks, right? Like that's what category theory is known to for mathematicians. And I think category theory is a language, and it's a language that you can make up and you can go as complex as you want. And it is, as a mathematical structure, the study of composition and abstraction. And I mentioned in the talk something like group theory. Once you're doing like Lie groups and symmetries, I mean they're super applied rotations for robots. But Riemannian geometry, there's like this Feynman quote about the mathematicians do Riemannian geometry to cover n equals 7, and then the physicists come along, they're like, oh, can you give me n equals 4 with like a Lorentz with a Lorentz metric, and then they get that and then they apply it, right? So these abstract things become applied if the characteristic nature of the problem matches the characteristic nature of the thing they're studying. For particle physics, it's all about symmetries. So group theory is now like, you just need it. General relativity, Riemannian geometry, you just need it. You could try to, and I mean, what we're doing with deep learning at the moment is sort of like trying to do general relativity without Riemannian geometry, right? It's like we can, but it's just we don't have the language. For Cutlass, and I think naturally it's just composition, reindexing. These reindexings are actually Hom functors, by the way. So that goes to the Annetta lemma. These are, this is like the bread and butter of category theory. It's like the Annetta lemma. It's composition. It's these rearrangements. So a Cutlass, when you read it, it's talking about composition and isomorphisms and all these things, but there are some parts of it that makes it not a coherent, as a category theorist, there's some parts of it which don't allow for the tricks which I think it should allow. And so, yeah, it seems like I think this will become, I think this is highly relevant. Otherwise, I wouldn't work in it. And I think other tools will converge towards this.
All right, thank you, Vincent. And I guess like sort of my last question to sort of close things off, which is like one of my main observations talking to you now, and especially throughout your talk, was like, at least within AI, like our attention span is like measured on the order of weeks. Like we basically look at like something interesting, figure out how to make it as fast as possible. Whereas like from a mathematician's perspective, like you have to have like sort of a longer term view of things, like develop the tools and basically essentially be patient and wait until they become like very useful. And then when they do, it feels obvious in hindsight. So like with this framing in mind, like what would you recommend for like the sort of average ML systems hacker that might be more familiar with like things like PyTorch and CUDA, and they're trying to get their feet wet with category theory, do some like interesting work with it? Like where would you recommend they get started?
I relate to what you say about the this is like, this project has taken years and like a lot of persistence. For getting to know category theory, if you're application focused, find an application where it's good. Hopefully we'll have a well, actually, if you're interested in engineering and category theory, my supervisor just wrote. His book was just released on applied category theory for engineering design, so people can check that out. And that covers category theory. It's for engineers. If you're doing deep learning, it's great. It covers the resource efficiencies, these like resource things and so on. It shows an application of category theory. Otherwise, find something you can apply to. Hopefully we'll get a formal write-up of all of this, and it can be a big tome. But hopefully the ultimate version of this won't require people to necessarily know category theory to be useful. So there'll be different levels at which you have to engage with the category theory. Hopefully we can derive theorems with guarantees, and then you can just play with the diagrams, and it should all be fine.
Yeah, like my suspicion is like, especially when you covered things like at what point do you index? Like, for example, do you do an operation, then index, or do you just index and then do the operation? At least like my wife, for instance, like works in databases. They have like a lot of like these ideas around like, should you sort of like push down or push up an optimization? And ideally you want to work with less data. So it does seem like the natural place for a lot of these intuitions feels like with compiler people, so that they could like naturally prove out that their optimization was correct. And then as these passes become more and more popular, my suspicion is that like they will sort of enter the mainstream. But at first, as compiler passes, to me, that also seems like a very natural uh, place to put a lot of these ideas in.
Definitely. Like what we're doing here is we're basically developing the mathematics for a compiler, right? A big step in this will be at some point, once we can derive the description of the algorithm to then go to implementing it, like turning it into CUDA code, turning it into PTX, or whatever else you want. We're working with compilers exactly as you say. Like there's lots of these shared patterns.
Excellent. Vincent, thank you so much for coming on. You're more than welcome to come by in again. So thank you for humoring us, and thank you, everyone. We'll see everyone next week. And thanks again,
Yeah,
Vincent.
that was fantastic. If anyone has questions, you fling me a message.
Excellent. Thank you
Yeah,
so much.
thank you.